Hey, let's check out some limits of multiple variable functions. We have several examples to go through. Let's look at the limit as x and y approach the point 0, 2 for the function e to the xy. As long as a function is defined, you can substitute your numbers in. 0 can go in for x, 2 can go in for y, and 0 times 2 is 0. E to the 0 is 1. Remember, E is Euler's number, so it's a positive irrational number. To the 0 power makes it 1. This one we have a radical underneath, so let's just make sure that 1 and 1 doesn't create a 0 under here. It does not. So we can direct sub 1 in for x, 1 in for y, and that gives us 1 over the square root of 2. This answer is totally fine. If you want to rationalize it, feel free. The limit as the xy pair approaches 1, 1 for this function, 1 times 1 minus 1, that's 0 for the numerator. 1 plus 1 times 1 gives us 2 for the denominator. 0 over 2 is 0. And then finally, if our ordered pair approaches 0, 0 goes in for the x's, also for the y. 0 squared is 0. 1 times 1 is 1, but overall 0. There are times where the limit won't exist, and now it doesn't always mean that you have a 0 denominator. There are times when you can have a 0 denominator and the limit actually does exist. For this one in particular though, because we have a fixed numerator, the closer you let x and y get to 0, the closer that gets to 0. In other words, a fixed numerator with a smaller and smaller denominator will actually make that fraction value take off to infinity. Positive infinity specifically, because whether you square a positive or a negative number, the answer will be positive, and the sum of two positives is also positive. Now, at exactly 0, 0, you can't evaluate this one because there's no way to use any math tricks to get this denominator to be removable or go away from it. So this is a limit that doesn't exist. It approaches infinity as x and y both approach 0. Now there are some tricks you can try, but for this problem it doesn't work. You can actually, because these are three-dimensional shapes, you can approach along the x-axis. You can approach the origin of this function along the x-axis. Now, in order to do that, you have to let the y value be 0 specifically, so that'll change your limit as the point x0 approaches 0, 0. But even when you do that, it leaves the x variable open. That's still going to be 1 over and smaller, very small number, so that one's not going to exist. You can also come in along the line y equals x. You can do it again along the x-axis like we did just then, But we can also come in from along the line y equals x. See, this line hits the origin just as well as the x-axis by itself does. If you try this path, you can replace y with another x. Replace y with another x. And that makes 1 over 2x squared, but you still run into the same problem, a fixed numerator with an ever-decreasing denominator. So that makes the value take off. Let's look at a piecewise function. Function f defined as this fraction as long as x and y is not at the origin. If the point is at the origin, it's defined as 0. Function g is just a repeat, but at the origin, it's defined as 10 instead of 0. Okay, so what we're going to do is we're going to take the limit of this common fraction that each function has, and I wrote that here, and we're going to see what happens as x and y both get close to 0. This numerator is a difference of two squares. It will factor as x squared minus y squared times x squared plus y squared. Well, we get lucky because that cancels down to just x squared minus y squared, and when you sub in the zeros, you get 0 overall. So that's what I was telling you on the previous slide. Just because an initial substitution gives you 0 in the denominator doesn't mean all is lost. Sometimes your problem can have a removable discontinuity, and that's the case here. Now, function f is appropriately defined to be continuous. Function g is not. And let's look at another example. The function g of xy is equal to 2 over y minus x squared. Now this function is going to be continuous as long as it's defined because it's a rational function. But if y is ever equal to x squared, then you get a 0 denominator. So this function is actually continuous at all points xy except for points on the parabola y equals x squared. That creates a 0 denominator. Recall that in polar coordinates, x is equal to r times cosine theta, and y is equal to r times sine theta. If x and y approach 0, that means r must approach 0 as well. Sine and cosine just oscillate up and down forever between -1 and +1. So if x and y ever have to go to 0, that r value must also go to 0. Now, let's go back to an example where a direct substitution yields a 0 denominator. On this one, we're not able to factor the numerator to get a cancellation with the denominator, and that's okay. Let's replace x with r cosine theta, both of those, and we're going to replace both of the y's with r sine theta. We can make those substitutions, and that's what I've done on this step, change from x and y to r. On the numerator, we get r cubed sine squared cosine theta. In the bottom, if you factor out r squared, that leaves cosine squared theta plus sine squared theta. Well, by Pythagorean identity, what's this equal to? That's right, it's equal to 1. If that's equal to 1, then you can cancel 2 of your r's into those 3, and that'll leave an r cosine theta sine squared theta, and when r goes to 0, the whole thing goes to 0. This value oscillates, this part oscillates between -1 and +1, and because sine squared is squared, this will oscillate back and forth from 0 to 1. When you square sine or cosine, it bounces instead of oscillating. It'll bounce. But that coefficient, the closer it gets to 0, no matter what these are, the smaller your answer gets. Another example using polar coordinates would be if we had to let 0 be the approach number for x and y. xy approaches 0. You can actually direct sub these because a radical, square root radical, is still defined for 0, and you can actually take the sine of 0. You don't have to use polar coordinates, but if you were to, you could replace this with r, because x squared plus y squared back up here would be the same thing we got in this denominator. And once you factored out r squared and take the square root of r squared, you would get r. So as r approaches 0, you have sine of 0, which is 0, and that just confirms it. This example, you actually don't have to translate and change them to polar coordinates, because 0 squared plus 0 squared is 0, square root still 0, and sine of 0 is 0. But up here, it definitely helps to change those out for polar coordinates. I hope this video helps you out. Let me know if you have any questions, phone, email, or swing by the office, or ask in class. And anyway, I hope this helps.